In this video, we're going to do some curve sketching. This is from section 5.4, which is about exponential functions, which is in the transcendental functions chapter of our calculus book. Basically, we're applying a lot of the techniques that we've discussed earlier this semester to this particular function. Now, this is a function from statistics. It's a very important function. It's called the normal probability distribution. We call it the standard normal probability distribution if this parameter, which is called the mean, is equal to 0, and this parameter, which is called the standard deviation, is equal to 1. But there are lots of other normal probability distributions with means other than 0 and standard deviations other than 1. But all of these functions basically have the same shape. So we're going to look at this function. We would like to sketch it. And when we sketch it, we want to sketch it in terms of those parameters, mu for the mean and sigma for the standard deviation. So let's do some curve sketching. First of all, let's talk about the domain. Well, this is just an exponential function. This is just a constant times an exponential function, and that constant is always positive. The standard deviation, if the standard deviation was 0, this constant would be undefined. If we had a standard deviation of 0, that would just mean all of the points in the data set have exactly the same value. And that usually doesn't happen. So if there's any variation in the data at all, this is going to be non-zero, and we're just going to have, or it's going to be actually positive, and we're going to have just some positive constant here. And then this is just an exponential raised to the e, or we have e to the negative x minus mu squared power, all divided by 2 times that standard deviation squared. So we're just dividing by a number. You've got x minus a constant squared. You've got a negative sign there. And we don't really have to worry about any problems. Usually when we're finding the domain of a function, we need to exclude any x values that cause division by 0, exclude any x values that cause even roots of negative numbers, and exclude any x values that cause logarithms of negative numbers or 0. And we don't have any of those in this case. So the domain is all real numbers. And now if I want to sketch the curve, usually the first thing that we do is we find the critical values of that function. To find the critical values, we compute the derivative of f. Now we're taking the derivative with respect to x of 1 divided by the standard deviation times 2 pi times e to this power. So the derivative of a constant times an exponential is that constant times the exponential. Oops, there should be a 2 in there. Now, anytime we've got something other than x in the exponent for an exponential, we've got to use the chain rule when we take the derivative. So the inside function in this case is this function, this whole thing. So when we take the derivative of e to that power, we're going to get e to that power times the derivative of the inside by the chain rule. And the derivative of the inside requires the chain rule as well. And we know it requires the chain rule because we've got this x minus the mean quantity squared there. And this -1 and that 2 divided by sigma squared, those are just constants. So we can factor that constant out. And then we say, okay, well, what's the derivative of x minus a constant squared? Well, it's just going to be 2 times the inside function, which is x minus mu in this case, times the derivative of the inside by the chain rule, and that's just a 1. The 2's reduce. And now I've got this negative 1 over sigma squared here. I'm going to factor that out and multiply it by this other constant. So I've got -1 over sigma cubed now times the square root of 2 pi times x minus the mean times e raised to that original exponent. All right, so that's our f prime. And whenever we're finding the critical values of f prime, we need to compute f prime, set it equal to 0 and solve for x. And then we also need to think about any x values where the derivative is undefined. And this is well defined all the time because this is just a negative constant now because our standard deviation is positive times a polynomial times an exponential. Polynomials are defined for all real numbers. Exponentials are defined for all real numbers, provided that what's inside them is defined for all real numbers. So this is defined all the time. So you don't have to worry about f prime being undefined. when we set f prime equal to 0 and solve for x, we say, well, this times this equals 0. The only way that equals 0 is if the first factor is 0, which never happens because that's just a negative number, or the second factor equals 0, or the third factor equals 0, but exponentials are always non-negative as well. Well, actually, they're always positive. This is always a positive number, no matter what x is. So the only way that this product could be 0 is if that polynomial term is 0. That means x must equal the mean. That is our one critical value. And we always have to ask ourselves, are there any x in the domain for which f prime is undefined? And say no, those would be critical values as well. But no in this case. So we just have the one critical value. And again, this is our normal probability distribution. So I'm expecting that sort of traditional bell-shaped curve. So now that we've got our critical value, we need to determine whether it's a relative minimum or a relative maximum. Because we're expecting that sort of traditional bell-shaped curve, which kind of looks like this. And sort of the center value where that maximum occurs is the mean. Because I'm expecting it to look like this, I'm expecting the first derivative to be positive on this side and then negative on that side, just because I'm familiar with what the normal probability distribution is supposed to look like. But let's actually do the calculus to make sure that that's actually what the curve looks like. So we know that f prime is 0 when x is equal to the mean. And let's determine the sign of f prime on various intervals. So to do that, we're going to make a sign chart for f prime. And then we list the critical numbers on the sign chart, or excuse me, list the critical numbers on the number line. I'll just say on a number line. And we just have the 1. And then we think about the sign of f prime on each of these intervals. Again, I'm imagining it's positive here and then negative here, but let's prove it. To determine the sign of f prime, I think of it as a product of this factor, and this factor. Well, this -1 divided by sigma cubed, and the square root of 2 pi is always negative because our sigma is always positive, provided that there is some variation in the data. This is going to be negative no matter what x is. This is a number line for x values. And then we say, okay, what about x minus the mean? Well, if x is greater than the mean, I'll have a number that's larger than mu minus mu, so it'll be positive. And if x is less than mu, let's say that mu is positive, then I'll choose x equals 0. So I'll have 0 minus mu is negative mu. That would be negative in that case. And then the exponential factor actually doesn't matter what you put inside that exponential. It's always positive. Because we know exponential functions look like this. Or if it had a negative exponent, well, and this one actually does, it would go the other way, right? Well, as long as we're not squaring it. The fact that we're squaring it is what leads to that sort of bell shape. But in any case, e to some power, no matter what that power is, if it's a polynomial power, is going to give us a y value that's above 0. So that exponential is always positive. Now f prime is this times this times this. So on this interval, it's a negative times a positive, which makes it positive. And then f prime is a negative times a positive, which is negative. So the function goes from increasing to having a 0 slope to decreasing. So by the first derivative test, our function has a relative maximum at mu. So f of mu is 1 divided by the standard deviation times the square root of 2 pi times e to the negative mu minus mu squared divided by 2 times that standard deviation squared with a variance. This is just e to the 0. E to the 0 is 1. So we have 1 divided by standard deviation times the square root of 2 pi is our relative maximum. And it's by the first derivative test. Okay, so we know that's true. And we're curve sketching. So let's find the second derivative and think about where that graph is concave upward versus being concave downward. Okay. And I guess before we talk about the second derivative, let's write down the intervals where the function is increasing and decreasing. So from this, f prime is positive on this interval, so the function is increasing on the interval from negative infinity to mu, and the function is decreasing on the interval from mu to infinity because that's what it means when f prime is negative. The y values are getting smaller as we go farther to the right. So we know that that's true, and now we're going to look at a second derivative. So we've got the second derivative of f is the derivative with respect to x of the first derivative, which is this negative 1 divided by sigma cubed times the square root of 2 pi times this polynomial factor times the exponential factor. And we've got our constant out front, so we'll just write that constant down, times the derivative of this product. So I'll use the product rule. Here's my first factor, and there's my second. So the derivative of a product is the derivative of the first, which in this case is 1, times the second. That's our exponential function. Plus the derivative of the second function, and the derivative of the second function we found earlier. Well, actually, let's just do that again. We'll use the chain rule. Oops, there's my highlighter. Here's my inside function. The derivative of e to some power is e raised to that power times the derivative of the inside by the chain rule. And that negative 1 divided by 2 sigma squared is a constant. So I'm going to factor that out. And say, okay, well, the derivative of e to this power was e to that power times the derivative of the inside. And then you say, how do I take the derivative of the inside? I use the chain rule again. So we'll have from here the derivative of a constant times some function squared is that constant times 2 times the original function. Because the derivative of function squared is 2 times the original function to the 1 less power. 2 minus 1 is 1 times the derivative of the inside, which is just 1. This is derivative of the first times the second plus derivative of the second. Don't forget to multiply by the first, which is that x minus mu. And all of that is multiplied by that constant out front. You say, okay, how can we simplify this? Well, the 2's reduce here. I notice I've got a negative factor here and a 1 over sigma squared here. I'd like to factor that out. So if I factor out a negative 1 over sigma squared from this term and this term, that's going to give me a negative times a negative is a positive 1 over sigma to the third times sigma squared is going to be sigma to the fifth. But be careful here. We didn't actually have a negative 1 over sigma squared for this expression. So you say, well, okay, well, what do we have to multiply this by? Or actually, what do we have to multiply this by so that the coefficient here as a function of sigma times this gives us this? Well, it's going to be a negative sigma squared. Because negative sigma squared divided by that sigma to the fifth is going to give me that negative 1 over sigma cubed. So I've got negative sigma squared times our exponential. And then I have that minus we factored out. So I've got an x minus mu times an x minus mu. So it's x minus mu squared times the exponential. And that's our f double prime. And we're again looking at this expression and this expression, and we see that they have that exponential in common. So we can factor the exponential out from everything. And I'm using scratch paper, so that's from another problem. Sorry about that. So f double prime is 1 divided by sigma to the 5th times the square root of 2 pi times the exponential factor. And then you say, okay, well, the exponential times what gives us this term? It's going to be that x minus mu squared. And then the exponential times what gives us the second factor, or the second term, excuse me, it's going to be that negative sigma squared. Now, if you want to, you could write that twice in FOIL, but I don't think it's necessary because we're ultimately going to set f double prime equal to 0 and try to find the x values that cause that second derivative to be 0. If f double prime changes signs at those x points, or x values, excuse me, and those x values are x coordinates of our points of inflection of the original function. So we'll set this equal to 0 and solve for x. And this is just allowing us to find those possible points of inflection, which is very similar to finding critical values. We also are always interested in where f double prime is undefined. We use that in our sign chart as well, but this is well defined for all real numbers. We just get an exponential times a polynomial times a constant. You say, okay, well, how is this equal to 0? Or when would this be equal to 0? Well, I've got a product. This product is 0 if the first factor is 0, or the second factor is 0, or the third factor is 0. But exponentials are always positive. This coefficient is positive when our standard deviation is positive, which we're going to assume it is. We're going to assume that there's some variation in our data set. The only way this is 0 is if this polynomial is 0. So we'll have x minus the mu, or x minus the mean, which is mu, squared minus sigma squared equals 0. And I'm solving for x, so I've got x minus mu squared equals sigma squared. Now we're going to take the square root of both sides. Now on the side with that sigma squared, we're going to put a plus or minus. So we have x minus the mu, or the mean, is plus or minus the square root of sigma squared, which is sigma, because sigma is non-negative and positive if the data set has any variation. The data has any variation. And then if we add mu to both sides, we get x equals mu plus or minus sigma. So there are actually two values there. It's the mean minus the standard deviation and the mean plus the standard deviation. So if we are interested in the sign of f double prime, we're interested in it on 3 intervals. And those intervals are separated by these two x values. So we have the mean minus the standard deviation and the mean plus the standard deviation. Or if you prefer, you can use the Greek letters that mu minus sigma and mu plus sigma. We're going to create a sign chart for f double prime. To determine where the graph is concave upward or concave downward. All right, so I've got that. Now, f double prime is this times this times this. And again, this factor and this factor are always positive. So it does not matter what x is. That's always positive, and the exponential is always positive. I'm just going to put some dots there. It's that exponent there. Maybe I shouldn't put dots there. We'll do that instead. And then we say, okay, the sign of f double prime is basically going to be determined by the sign of this factor because it's the only one that's not positive all the time. It's sometimes positive and sometimes negative. We've got x minus mu squared minus the standard deviation squared. Now, if I want to, I can think of this as a parabola. I can think of this as y equals x minus the mu, or x minus mu squared minus sigma squared. So that means it's going to look like y equals x squared. And we're just shifting mu units to the right and then negative sigma squared units downward. So it's roughly going to look like this. And then it intersects the x-axis at mu minus the standard deviation and mu plus the standard deviation. And you say, okay, well, what is the sign of this x minus mu squared minus sigma squared? Well, it's going to be the sign of the y values on this graph. So on this interval here, we see that our function values are positive, and our function values are positive over there as well. So if we are beyond this x mu minus sigma and mu plus sigma, either to the left or to the right, the y values on that parabola are greater than 0. And then you say, okay, well, what about in between? Well, obviously, if you reread this graph, below the x-axis, the y values are negative. So here is where our y values are negative. So the sign of this factor is positive on this interval, negative on this interval, and positive on that interval. And f double prime is the product of those. So f double prime is a positive times a positive times a positive, which makes it positive. And then we've got a positive times a negative, which makes it negative. And then it's a product of 3 positive numbers, which makes it positive. That means the original graph is concave upward, then concave downward, and concave upward on each of those intervals, because f double prime being positive means the graph is concave upward, which looks kind of like a cup facing up. And f double prime is, when f double prime is negative, it's going to be concave downward, which looks a little bit like a cup facing down. Now, on these intervals, you might say the graph, the bell curve that we were expecting to graph from this doesn't look like this. It doesn't have like this shape. And you're right, it doesn't. If we actually look at our calculations from earlier, we see that f prime is positive to the right of 0, or excuse me, right of the mean, and then negative to the left of the mean. That means the original function is increasing here and decreasing here. So when we look at the second derivative and we try to graph the function, we have to keep that in mind. We're saying, okay, when we're below the mean, which is over here, our function is increasing and concave upward. So it's going to look like the right half of that parabola. And then over here on this side, the function is decreasing in concave upward. If it's decreasing in concave upward, that's on that left side of that parabola. I don't know if I said that correctly. I think I said left here when I meant right. But increasing concave upward is going to look like the right half of that parabola. Decreasing and concave upward is going to look like the left half. And on this interval, when it's concave downward, the mean is like right in between that the mean minus the standard deviation, the mean plus the standard deviation. So the mean is right here. And the function is increasing concave downward and then decreasing concave downward. And that's exactly what we see when we look at that sort of parabola representing the function. They say, okay, well, the f double prime changes signs at this location and this location. So those two x values must correspond to points of inflection of the original function. So we'll say since f double prime changes signs at x equals the mean plus or minus the standard deviation. These are the x coordinates of f's points of inflection. So we create a sign chart in the same way as before, looking at the sign of each factor of f double prime on each of the intervals. Find the signs, multiply them together to get the signs of f double prime. And then we infer from there where the graph is concave upward and concave downward. And then we use those changes in concavity to identify points of inflection. Now, point of inflection has to be in the domain. So you want to make sure that you're talking about x values in the domain of the original function whenever you're finding points of inflection. There might be an x value on this number line where f double prime was undefined, and therefore we put it on the number line. Those would not correspond to points of inflection, but these are in the domain of our function, so they do correspond to points of inflection. So let's evaluate f at those points of inflection now. We have f is equal to 1 divided by that standard deviation times the square root of 2 pi times e to the negative x minus the mean squared, all divided by 2 times the standard deviation squared. And we are evaluating at the mean plus or minus the standard deviation. Now, when we do that, the means reduce. And this is plus or minus the standard deviation squared. So you're going to have the standard deviation squared times -1, all divided by 2 times the standard deviation squared. We actually call that the variance. Those reduce. And we have 1 divided by sigma times the square root of 2 pi times e to the negative 1/2. And one thing I want you to notice about this is the points of inflection depend on that parameter sigma. And it does not depend on the mean at all. If our sigma is larger, those points or those y values are going to be smaller. So the graph is going to be sort of like squatter. It means just that the graph, the original data set is more spread out. Now, another thing is that relative extrema, that was a relative maximum that we had at the mean that was right here. We could have used the second derivative test to find that. If we evaluate this expression at x equals mu, sorry, there are calculations from a different problem in there. If we evaluate the second derivative at x equals mu, we get e to the 0 here, which is 1. And then we've got 0 squared here. And then we have this negative sigma squared times this. So we end up with a -1 divided by sigma cubed times the square root of 2 pi. That shows us that at x equals mu, the second derivative is negative. So the graph is concave downward, and we're at a point where the derivative is 0, so we must be at a relative max by the second derivative test. So the second derivative test tells us that x equals mu corresponds to a relative max, just like the first derivative test does. So I think I will do that just to make that clear. So I have f evaluated, or f double prime evaluated at mu equals this times e to the 0 squared divided by 2 times sigma squared. So this is just e to the 0, which is 1, times 0 squared minus sigma squared. It's actually a 0. It looks a little bit like a sigma. That gives us that -1 over this. So we'll say since f prime at mu equals 0 and f double prime at mu is a negative value, the graph looks like this. We're at the top. F of mu is a relative max. So the second derivative test tells us it's the same thing that the first derivative test tells us. Again, the x coordinate of that relative maximum actually depends on the parameter mu. So if we look at this graph, or if we look at this function, if we take our x's and we subtract mu from them in this formula, if rather than having an x squared here, I have an x minus mu squared, that just means I'm changing the, I'm just shifting the entire graph mu units to the right. So that represents just a horizontal shift. And changing the value of sigma, which is a standard deviation, will like spread out our data, as we'll see. Okay, so what did we want? We wanted to identify points of inflection. We did. We wanted relative extrema. We determined them using the first derivative test, and then we confirmed that our answer was the same using the second derivative test. We wanted to know where the graph was concave upward versus concave downward. And this tells us that. So we know that the graph is concave upward on those two intervals on the end, from -infinity to the mu minus the standard deviation and mu plus the standard deviation to infinity, and concave downward in the middle. Okay, and I think that's enough to graph our function. We could graph our function by hand using this information. But we might also be interested in graphing it using a calculator. This is what I get if I graph my function by hand. Here's my mu. And what was that maximum value? I lost my, was that 1 divided by sigma times the square root of 2 pi? Was that it? I think it was. And then we have the mu minus the standard deviation and mu plus the standard deviation. And the y values there were this number times e to the -1/2. And again, as sigma increases, that maximum value decreases, because 1 divided by a larger number is going to be a smaller number. Okay, so our graph roughly looks like that. We have got those 3 points on it, and it's increasing on this side, decreasing on this side, and it's increasing in concave upward. First derivative is positive, and the second derivative is a positive as well. So increasing in concave upward looks like that. On this interval, it's increasing in concave downward. On this interval, it's decreasing in concave downward. And then on this interval, it's decreasing and concave upward. And that is the normal probability distribution. Very important function from statistics. Areas under the curve tell us sort of they give us the probability that a particular random variable lies between a particular number of standard deviations below the mean and a particular number of standard deviations above the mean. Let's look at this graph online and see that our picture online is consistent with everything that we've discussed. Now, when I created this Desmos, I'm going to call it a notebook. I really don't know what to call it. I guess it's just a web page. Desmos tends to refer to these as graphs, but there's so much code on the left-hand side, it feels more like graphs with text and formulas. So in Mathematica, I would have called it a Mathematica notebook, but now we're calling it, I guess, just a page. It's just a web page that I'm saving online that has my graph and all the notes. So this is the formula. Now, because Desmos doesn't have the ability to, or does not allow us the ability to type Greek letters, I'm using M for the mean and S for the standard deviation. Usually those letters are reserved for something else in statistics, but these are the letters that we're using in this particular notebook. So we wanted to find the relative extrema, points of inflection, intervals where the function's increasing, decreasing, and all of that. And I think we did. I think we can see that it's concave upward until we get to that 1 standard deviation below the mean, and it's concave upward and increasing, then concave downward on that interval in the middle, concave downward and increasing on the left-hand side of that middle point, concave downward and decreasing on the right-hand side, and then as we go from that 1 standard deviation above the mean to infinity, the graph is concave upward and the function is decreasing. So this is what our graph looks like for the normal probability distribution with a mean of 0 and a standard deviation of 1. But we could change the mean and we could change the standard deviation. One variable that is normally distributed is IQ. So we could change the mean to 100 and the standard deviation is approximately 15. Now we can't even see the graph, but if we wanted to, we could do that. Let's go to, we want our x values to be between, let's say 55 and 150. And then we want our y values to go up to that value right there. Let's say so that's roughly the shape of it. But notice how small that y value is. It turns out we still get an area of 1 under the curve because the probability that somebody has an IQ is 1. They have some IQ. And that IQ it has a tendency to be centered at 100. That's the average. And then we add or subtract 15 to get 1 standard deviation from the mean. So 1 standard deviation below the mean for IQ is 85. 1 standard deviation above the mean is 115. And we have this area here. But one thing I want you to notice is that I can change the shape of this graph by changing the value of the standard deviation. If my standard deviation is smaller, it's sort of taller. If my standard deviation is large, I can make it wider. The mean just moves it back and forth. So we're changing that center point. But the area under the curve remains the same. So all these normal probability distributions have the same basic shape, but the area between a certain number of standard deviations and another, like between one number of standard deviations below the mean and another number of standard deviations above the mean usually. And they don't have to be on the left and right of the mean, but usually they are. Between those two values is the same, regardless of the value of mu and the value of sigma. But let's go back to where we were before. Let's have a standard deviation of 1 and a mean of 0. If we look at that, let's let our x values go from negative 3.5 to 3.5. So I want to go plus and minus 3.5 standard deviations. And then I think we want 0.1 here, and let's do 0.5 there. So that's what our graph looks like. And you say, well, what is that 0.3989 equal to? Well, that was that 1 divided by the standard deviation times the square root of 2 pi. Since the standard deviation is 1, we've got 1 divided by the square root of 2 pi there, which is that number. But of course, that's going to change as s increases. If s is larger, let's say s is 2, now it's half as tall. If s is 4, it's going to be 1/4 as tall. If s is 1 again, we've got that. And so changing the s value effectively changes the shape of the graph. And we are not interested in negative standard deviations. It's always if there's any variation at all, it's always positive. If there's no variation, then the standard deviation would be 0, but that would be a very boring data set where all the data are exactly the same. Okay. So we computed the first derivative, and we did all this on paper. We created our sign chart for f prime. We could have just as easily graphed f prime. So here's what f prime actually looks like. It's kind of cool. Got an exponential times a polynomial times a function, a negative coefficient. And when we look at this in this way, we can see that f prime is equal to 0 at 0, and f prime is positive to the left of 0 and negative to the right. So with that, we can say, okay, if f prime is positive, then the original function should be increasing, and it is. And if f prime is negative, then the original function should be decreasing, and it is. Now, the relative extrema of f prime correspond to points of inflection. That's where the second derivative is 0 and the first derivative is changing from increasing to decreasing. So at that 1 plus or minus 1 standard deviation from the mean, we see that our first derivative has a maximum and our first derivative has a minimum here. Since our first derivative has a maximum, that means the first derivative is going from increasing to having a zero slope to decreasing. When the first derivative is increasing, that means our second derivative is positive. So the graph is going to be concave upward. When the first derivative is decreasing, that means second derivative is negative. So the graph is going to be concave downward. And we see that it's the first derivative is decreasing from -1 to 1. So from 1 standard deviation below the mean to 1 standard deviation above the mean. And then from 1 standard deviation above the mean to infinity, the function's increasing again, or f prime is increasing again. When f prime is increasing, that means the second derivative is positive, so the graph is concave upward. But we can see all of that. We can see the relative extrema. We have a relative max at 0 because f prime goes from positive to negative. So the function goes from increasing, having a zero slope, to decreasing. And then those extreme values of f prime correspond to points of inflection, as the graph goes from concave upward to having a second derivative of 0 to being concave downward, and then concave downward to having a second derivative of 0 to concave upward. And we plotted those points. Here's a second derivative. Looks like that. And we see that that's consistent with what we just talked about. Second derivative is positive from negative infinity to -1. So the graph is concave upward. Second derivative is negative from -1 to 1. So the graph is concave downward. The original graph is concave downward. And then the second derivative is positive from 1 to infinity. Now, if we change the mean or the standard deviation, again, that does not change those relationships. Those relationships relative to the mean and the standard deviation remain the same. So let's say instead of having a mean of 0, I had a mean of 3. Well, then just shifts the graph 3 units to the right, but the second derivative still looks the same, right? So we still have those points of inflection plus or minus 1 unit from the mean. The mean just happens to be 3 now instead of 0. And if I change the standard deviation, instead of having a standard deviation of 1, I have a standard deviation of 2. I'm going to add and subtract 2 from 3 to get those points of inflection. And you see that's what we get here. 3 minus 2 is going to give us 1 standard deviation below the mean. And then 3 plus 2 is going to give us 1 standard deviation above the mean. Now my claim is that area under the curve is the same. Regardless of what I do to that S value, this area here is the same as that area there. And shifting it back and forth, well, it doesn't change the area at all, right? That's why we can just focus on that standard normal distribution, the one that's centered at 0 and has a standard deviation of 1. If we understand this one, then we kind of understand them all, as long as we know how the standard normal distribution is related to the other non-standard normal distributions. And those are just ones that have different means that are not 0 and standard deviations that are not 1. All right. So we're in calculus class. You say, okay, how is this relevant? Well, it's kind of cool. You get to see this curve and think a little bit about how it might relate to statistics and probabilities. Take that class if you're interested in that. It's an excellent class. It's elementary. I mean, well, I'm going to say it's a junior college class, but it transfers. So you still have to know what you're doing. What I was going to say was it is an introduction to statistics. So we've got that. Now, another thing that we might be interested, because we're in calculus and because we've already learned, we've learned about derivatives, we've learned about the first and second derivative, and points of inflection, relative extrema. We've also learned about integrals. We've learned about area under the curve, and these areas correspond to probabilities. I mentioned that non-standard normal distribution for IQ. So the non-standard normal distribution for IQ had that mean of 100 and the standard deviation of 15. So I would have 15 here, or 100 in the middle, and then I'd have plus or minus 15 from that in the left and right. So we'd have an IQ of 85 and an IQ of 115. And then to go from plus or minus 2 standard deviations from the mean, then our IQs would go from like 70 to 130. You might be interested in, like, well, what is the proportion of people in the population that actually have IQs between 85 and 115, or actually have IQs between 70 and 130? Or maybe you're interested in those that have an above average IQ from 100 to 130, or 100 just anything, well, anything to the right of the mean is going to be 50%, obviously, because it's the area there. But we can find all of that if we know how to integrate. And this is actually a function that's very difficult to integrate. Let's look at this function. Now, assume the mean is known and the standard deviation is known. If you want, you can let the mean equal 0 and the standard deviation equal 1. But if you do, you see that you've got that basically an e to the negative x squared. And you say to yourself, do I have a rule for that? Well, if I had an x out front, I'd be able to integrate using u substitution, but I don't have an x. The derivative of that negative x squared would be negative 2x. In order to use u substitution, I'd need a multiple of negative 2x multiplying this function. But I don't have anything like that. So you might say, how do we find that area under the curve that's so important, that's giving us those probabilities for normally distributed random variables? And you'd say, well, one way you can do that is you can evaluate that integral numerically. So we're going to do that. So this is problem 2a. I'm going to undo what I just did. There we go. This is problem 2a. Basically, we're going to integrate. We're going to find the area under the curve using the trapezoidal rule, that numerical method that we studied in Unit 4. But again, I want you to see that that area under the curve is unchanged when you change the standard deviation. Changing the standard deviation, again, changes how much you're spreading that curve out. Just if the standard deviation is larger than 1, it's going to be wider. If it's smaller than 1, it's going to be skinnier. So if I made it less than 1, see how I make it making it skinnier and taller. Greater than 1, it makes it sort of wider and flatter. But I claim that the area under the curve from one particular number of standard deviations relative to the mean to another, that's going to be the same no matter what. Here is a table of values that allows us to see sort of what happens with that. I've defined this function. We're integrating from the mean minus some number of standard deviations to the mean plus some number of standard deviations. So I'm looking at area in the middle, but we don't necessarily have to do that. It doesn't have to be symmetric about the mean. It's just something that we have a tendency to think about. So if we're looking at adding and subtracting 1 standard deviation from the mean, this area under the curve is 0.68. So that means that like 68% of normally distributed data lie between one standard deviation below the mean and 1 standard deviation above the mean. So with that IQ example, we're saying 68% of the population have IQs between 85 and 115. And then when we have b equals 2, and I'm using b instead of n here, that's going to give us 95% of that area. The area under the curve is 0.95, approximately 9545, or almost 95.4% of the area. It turns out the area under the curve is 1. And we'll be able to prove that once we learn about improper integrals in calculus 2. But actually, will we? I don't know. Anyway, I think we actually have to wait till calculus 3 to show that that is going to be, I don't know. And anyway, I'm sorry, I'm getting distracted. But it turns out that this area under the curve from 2 standard deviations below the mean to 2 standard deviations above the mean is 0.95. So that means the proportion of people, just using my IQ example, with IQs between 70 and 130 is that like 95.4%. The 95.4% of the population has IQs between that 70 and 130. And then when you say, okay, what about, if I subtract 15 and add 15 again, so what about IQs between 55 and 145? There'd be 99.7% of the population would have IQs on that range. And if you look out to 4 standard deviations above the mean and 5 standard deviations and 6, eventually Desmos says, it's so close to 1, I'm just going to call it 1. If we zoom out a little bit, we can see that the Y values on that bell bell-shaped curve, that graph of our normal distribution, are so close to zero at x equals -6 and x equals +6 that they might as well be zero. But we can find the area value for different values of b just by changing this, like moving this slider back and forth. And if you want, you can get rid of that n here. I'll just say b equals 1. I'll put a b here and a b here. And when I do that, you can say, okay, that's giving me that area of that 68%. And then you say, okay, well, what if I'm -1.7, or I've got the mean minus 1.75 standard deviations. I'm interested in data between -1.75, well, how do I say it? I'm interested in data between 1.75 deviations below the mean and 1.75 standard deviations above the mean. Well, what's the area in that case? Well, it's about 92%. So 92% of values of that normally distributed variable lie between that 1.75 standard deviations below and above the mean. And so you can change the value of b, and then you can visualize that. And I've just got b between 0 and 3. I have a tendency to use b between 0 and 3 or 3.5. This 3.5 is giving us an area that's so close to 0, it might as well be 0. Oh, thank you so much. Oops. Okay. So I'm going to go back to calling that 1, and then let area be a function of n, and putting an n here and an n here. There's something a little like wonky going on with the code in the background. I'm not really sure what it is. All right. So we've graphed that, and you say, okay, how do we actually find that value? If I didn't have Desmos telling me what the area was, how could I find that using calculus? Well, we can use the trapezoidal rule. So remember to do that. We create linear approximations of the function on various intervals. Now, if I'm looking at 2 standard deviations above and below the mean, I'm going to let b equal 2 again, rather than 1. That's the area I'm looking to approximate. That area right there. And say, okay. That means I need to take my interval from the mean -2 standard deviations to the mean +2 standard deviations. And I'm going to divide that by 4. If our mean is 0 and our standard deviation is 1, my tick marks or my x values are x sub 0 equals -2, x sub 1 equals -1, x sub 2 equals 0, and so on. So our x values are -2, -1, 0, 1, and 2. And then we'll graph the function on various intervals. Now, in each subinterval, we're going to create a line segment approximating the function. And that's just the secant line. So the slope that I'm using there is that change in y divided by change in x, using these two x values on our, or these two xy pairs, the xy pair at -2, and then the xy pair at -1. So -2, f of -2, -1, f of -1. And then I just graph it from -2 to -1. But I wrote everything in terms of the mean and the standard deviation so we could vary those and the line segments would still be in the right place. And we do that on the next interval and the next interval and the next interval. It's all pretty much the same. Just make sure to use the right points. We have that. And so we're approximating this area under the curve with the area under those line segments. Now, Desmos already gives us what's close enough to the exact answer. But if we wanted to calculate that numerically using the methods that we've discussed, we'd say, okay, well, what's the area of this little trapezoid? Well, it's 1/2 base times, or 1/2, the sum of the two bases times the height. Well, if we're sort of looking at this thing on its side, the height is that delta x, which is 1. And the two bases are the function value at -2 and the function value at -1. So we're going to have 1 times 1/2. 1 times 1/2 of the sum of those bases. So that's f of -2 plus f of -1. And then on the next subinterval, we're going to have 1/2 times delta x, which is 1, times the sum of the bases. That's going to be f of -1 plus f of 0. So we're counting that f of -1 twice because it's a base for the first trapezoid and the second trapezoid, but f of -2 is only included once because it's only included in that first trapezoid. So f of -2 and f of +2 are only going to be counted once. F of -1, f of 0, and f of 1 are included twice because those are boundaries to two trapezoids. They get included as the left base for the first trapezoid, and then the right base, or the right base for the first trapezoid, and then the left base for the trapezoid to the right of that. So we have this formula. We've got 4 trapezoids, so we have 5 data values, 5 x values, right? So we double all of those in the middle because those are the ones that we count twice, and then we just evaluate the function once at the endpoints. And then this is 1/2 of that b minus a divided by n. That's our delta x. And b minus a is just the mean plus 2 standard deviations minus close or open quantity, the mean minus 2 standard deviations. So when you actually do that, you just get 4 times the standard deviation divided by 4 in this case. And look, we get an approximation of 0.9368. Say, okay, well, how is that related to the exact area? Well, the exact area is 0.954 approximately. And if we take the difference between those, we get an error of 0.017. So we see that's a pretty good error. Now, there's actually a way to, there's a maximum area formula for the trapezoid rule. We can say, okay, how many subdivisions do we need so that we are approximating that area under the curve with a certain accuracy? Well, we could use that in order to find the value of n, the number of subintervals we would need to get to the accuracy that we want. But since we have a way of calculating that integral numerically anyway, which is Desmos, we can take the difference between the Desmos's calculation and our approximation using the trapezoid rule. And we see that it's pretty small. It's 0.0176. So if we're comfortable with having a true value of that area under the curve that is within 0.0176 units of the true value, then that's an acceptable approximation. And if you say, I want my error to be even less than that, well, just take more trapezoids. Instead of using 4 subintervals, you might use, 8 subintervals or something like that and do that. All right. So that's the trapezoid rule. Now, we've also studied Simpson's rule. So now I might want to find the area under this curve from 2 standard deviations below the mean to 2 standard deviations above the mean using Simpson's rule. And remember, with Simpson's rule, you have to use an even number for n, because you're actually taking what would traditionally be 2 subintervals and you're creating 1 subinterval. So in our case, if we use n equals 4, we're actually creating sort of 2 larger, we're taking that n equals 4 and we're subdividing it into 2 pieces. We're saying, let's look at the first 2 subintervals together and then the second 2 subintervals together. And then we're going to use the xy pairs at the 3 function values associated with those 2 subintervals. So we'll have f of, or the xy pair at x equals -2, then the one at -1, and then the one at 0. And we will create a second degree polynomial that passes through those 3 points. If we use those 3 points, we end up with 3 equations and 3 unknowns, and the unknowns are the coefficients of the polynomial. If our polynomial is ax squared plus bx plus c, we're solving for a, b, and c. We can find those exactly if we have 3 points. So we'll do that. This was actually for n equals 8 subintervals. So I'm going to try to do this again with n equals 4 subintervals. With n equals 4 subintervals, we want our x values to be the mean minus 2 standard deviations, and then the mean minus 1 standard deviation, and then just the mean. And then we've got our function values there. And then we want to approximate f with just a second degree polynomial function. So we're using that tilde. That's how we sort of code the regression functions in Desmos. And then I've called the coefficients a sub 1, b sub 1, and c sub 1 because I'm talking about that first polynomial. So I want to use this first polynomial on the interval from the mean minus 2 standard deviations to the mean itself. So I'm going to use these 3 points, that point, and that point, and actually we should have graphed them. So you see those purple points there? And that's my polynomial. And I want to graph that from 2 standard deviations below the mean to the mean. So we're using that second degree polynomial to approximate our function. And then you might say, okay, I'm also, if I'm just using 4 subintervals, we could do the same thing on the other side. We'll use the function values at 0, 1, and 2 this time. So we'll have, we're starting with an x value at the mean, and then we want to be 1 standard deviation above the mean, and then we want to be 2 standard deviations above the mean. Oh my God. Okay. And I think we see some symmetry. We can see that the y value at 2 is the same as the y value at -2. The y value at 1 is the same as the y value at -1. And then we'll use Desmos to calculate the coefficients for that polynomial that fits through those 3 points. So we've got that. Then we graph that. And I did that for 8 subintervals last time on this one. It actually accidentally got edited. I wanted to show you 4, and then we'll show you 8 on the next one. All right, so the code for n, the Simpson's rule with n equals 4 subintervals is shown below. So we're going to have b minus a divided by 4, that's the number of subintervals, times f of x naught plus 4 times f at x1. Then we've got 2 times f at x2 plus 4 times f at x3. And then for 4 subintervals, the last one would be just f of x sub 4. And that's just code. It's asking me to add sliders for those. I don't want to add sliders. I actually haven't defined those, so I'm just going to leave that alone. With n equals 4, this is what we get. B is the mean plus 2 standard deviations. A is the mean minus 2 standard deviations. This is what we get for 4. We get an area of approximately 0.972. And for 8, we get 0.9544. Actually, Simpson's rule with n equals 4, it looks like that. And then the error is 0.007. Something. This was all supposed to be in part C instead of part B, sorry. Now you might say, okay, what about higher degree polynomials? How could we improve the approximation? Well, you could use a larger value of n. Remember, n has to be even with Simpson's rule. So we could use n equals 6 or n equals 8 or n equals 20 if we want. It might take a long time to write all the code for that. There's got to be a more efficient way than the way I'm doing it right now. But something that would allow us to find all of those polynomials for the n in general. But I actually don't know how to do that in Desmos. But you might say, okay, well, if it's a second degree polynomial, wouldn't we get a better approximation if we approximated it with a third degree polynomial or a higher degree polynomial? Especially when I look at this interval from -2 to 0, does it look more cubic as opposed to looking like a quadratic function? It looks more like a cubic function than a parabola, doesn't it? I'd really like to approximate it with a cubic and say, well, that'd be nice. But the cubic polynomial is going to have 4 coefficients, a, b, c, and d, right? Ax cubed plus bx squared plus cx plus d. In order to find those, we would need 4 equations with 4 unknowns. So we'd need more than 3 points. We need at least 4 points in order to approximate the function with a cubic polynomial. So if you want to approximate the function with an nth degree polynomial, you'd need n points. So we probably don't want to do that. Excuse me. All right. But you might say, okay, let's say I want to know, or I want to find an n value to make my error, my maximum error, as small as, well, not as small as possible, but like to make my maximum error less than a specific value or a given value. We can make the error as small as we wish by taking n large enough. And we had a theorem that we talked about when we discussed Simpson's rule that told us that the upper bound for the error was this b minus a divided by 180 times n to the fourth times the maximum value of the fourth derivative of the function. So if I want to know, or if I want to require that the estimated area with Simpson's rule is within 0.0001 of the true area, I can require this maximum value to be less than 0.01. So we have the actual error is less than or equal to b minus a raised to the fifth divided by 180 n to the fourth times the maximum of the absolute value of the fourth derivative on the interval of interest. So on the interval from a to b. Now we can find that value of n using pencil and paper calculations, and then we can sort of graph our fourth derivative and the absolute value of the fourth derivative on Desmos. Let's do that. So this is our second derivative. In order to find the maximum value of the absolute value of the fourth derivative, of course, I need to compute the fourth derivative. So, oops. This requires a product rule. Here's my first function. There's my second. So when I take, and this is the second derivative that we calculated earlier. Find the third derivative, we're going to have that constant out front times the derivative of the first times the second. Now the derivative of an exponential is always that exponential times the derivative of the inside. Now I'm going to factor out that exponential immediately because I know I'll have that exponential as a factor for both of the terms when we compute the derivative using the product rule. So we're going to have the derivative of the first times the second. The derivative of the first is e to this power, which is right there, times the derivative of the inside. Now when I take the derivative of the inside, I have to use the chain rule. Because I've got that x minus mu, it's being squared, and it's multiplied by this -1 divided by 2 times sigma squared. So that's a constant. And the derivative of x minus mu squared is 2 times x minus mu. So it's 2 times the inside function, right? Times the derivative of the inside, which is 1. So this is the derivative of the first is this times this, and then we say times the second. Plus the derivative of the second. There's not really enough room there. The derivative of this requires the chain rule as well. So we're going to have 2 times our inside function, which is x minus mu. And then the derivative of sigma squared is 0 because it's just a constant times the first, and that's right there. So since I've got this exponential factor, I just wrote the derivative of the inside times the second plus the derivative of the second. And then the first function was actually a factor of both of them, and I factored it out. I hope that makes sense. Okay, so this is what we've got. Notice I've got an x minus mu factor here and an x minus mu there. I've got this -1 over sigma squared here. So I'm going to factor out a -1 over sigma squared. It's going to give us a -1 divided by sigma to the 7, and square root of 2 pi times from here. I've got x minus mu times that x minus mu squared minus sigma squared. And then when I factored out that -1 divided by sigma squared, that's going to affect this factor. I need to multiply it by negative sigma squared so that when I take this -1 times sigma squared and I divide it by that -1 times sigma squared that I factored out, I just get that positive coefficient of 2 here. And we're multiplying by that exponential again. Sorry, my paper is sort of flying up. I'm trying to weigh it down with that. All right, so I've got this. If my text is going up, that means I must be excited about something. Now, when we look at this expression and this expression, they both have an x minus mu in common. So you can factor that out. Actually, I think what I'll do is I'll distribute it. I've got x minus mu times x minus mu squared is going to be x minus mu cubed. And then I have x minus mu times negative sigma squared. And then I've got 2 of those over here. So I'm going to have negative 3 of those. Times that exponential factor. Okay. So that is our third derivative. Okay, well, I really want a fourth derivative. So let's compute the fourth derivative. So I have our constant here. And then we're going to have derivative of the first. This requires a chain rule again. You've got that x minus mu as a factor. So we'll have 3 times x minus mu squared times the derivative of the inside, which is 1. And then the derivative of this piece with respect to x is just 1. And then we're subtracting that 3 times sigma squared. That's the derivative of the first. And then we're multiplying by the second. I'm just going to put dot, dot, dot for the exponent. Derivative of the first times the second plus the derivative of the second, which is that exponent times the derivative of the inside, which is that negative 1 divided by 2 sigma squared times the derivative of that 2 or x minus mu squared, which is 2 times x minus mu times the derivative of the inside, which is 1. That's the derivative of the second. And then we're multiplying by the first, which is that cubic polynomial. It goes there. Okay, so I notice I've got these exponentials in common when I look at this expression and sort of this expression. So I can factor those exponentials out. I get negative 1 divided by the sigma to the 5th times the square root of 2 pi. And then I have that exponential, and I think I'll write the exponent this time. And then we've got, well, we can factor out a 3 from this as well. Well, maybe I don't want to factor out a 3. I'll just leave that alone. I've got 3 times x minus sigma, or excuse me, x minus mu squared minus 3 sigma squared. That times the exponential gives us that expression. And then over here, we've got the exponential, which we factored out, times negative 1 over sigma squared times x minus mu times that cubic, which was x minus mu cubed minus 3 sigma squared times x minus mu. So many brackets and parentheses. But let's factor out negative sigma squared from everything. Like, did I make an error? I think I may have made an error. So if I factor out a negative 1 over sigma squared from this, I'm going to have a positive 1 and then a sigma to the 9th in that denominator. That's going to give me a negative sigma squared times this first factor. And then we'll have a negative sigma squared multiplying that. So it's going to give me a sigma to the 4th. And then I'll have a positive x minus mu times x minus mu to the 3rd is x minus mu to the 4th. And then this times that is going to give me, I've already factored this out, or actually another negative 3 sigma squared times x minus mu squared. I'm wondering if I'm doing this right. I hope I am. All right, this is what we've got. And I can, I see some like terms here. It's a lot of hand calculations. got x minus mu to the fourth minus, I've got 3 of those there and 3 of those there, so I've got 6 of those. That's my fourth derivative. You can say, okay, well, where is it maximized? Well, this is always positive and this is always positive. Well, actually, the fact that it's always positive doesn't matter. This is actually going to be, well, it's symmetric, isn't it? Anyway, we need to look at the absolute value of this. And we're interested in this on the interval from the mean, the mean minus 2 standard deviations to the mean plus 2 standard deviations. We want to maximize this function. So you say, okay, well, where do I find the maximums? Well, we'll find a maximum. Well, in order to find the maximum, we actually have to take the fifth derivative. So the fifth derivative equal to 0, and then think about when the fifth derivative changes signs. You're like, oh my goodness. Do I have to? Yes. So our goal is to find the maximum of this. On this interval, we know it exists because of the extreme value theorem. Let's compute the fifth derivative. A little bit tedious, isn't it? Product rule again. Here's our first function and our second function. We have the derivative of the first. So we're going to have e to that power times the derivative of the inside. The derivative of the inside is that constant times the derivative of that x minus mu squared, which is 2 times x minus mu times the derivative of the inside, which is a 1. That's the derivative of the first. And then we multiply by the second, which is that fourth degree polynomial. And we're adding the derivative of the second. We'll have 4 times that quantity cubed times the derivative of the inside, which is 1. And then we've got this, it's a constant, and then we multiply by the derivative of x minus mu squared. That's going to give us a 2 times x minus mu. So we'll have a negative 12 times x minus mu there. And then the derivative of this piece is 0. So that's the derivative of the second, and then we're multiplying by the first. Pretty much every time you've got an exponential factor and you're using the product rule, you're going to see that exponential factor twice. So if you're familiar with that, you can just sort of factor that out immediately. That's what I usually do, but I wanted to try to show my work because when I did that earlier in the video, I was like, I don't know if the students are going to follow that very well. So we've got that factor times the exponential. And then I've got a negative x minus mu, or this negative 1 divided by sigma squared times x minus mu times all of this. And I want to get rid of that fraction. So I think I will multiply by negative sigma squared out here. So I'm going to have a negative 1 divided by sigma to the 11th. And then I end up with just multiplying this expression by x minus mu. So I end up with x minus mu to the 5th. Minus 6 sigma squared times x minus mu cubed plus 3 times sigma to the 4th times x minus mu to the 1st. And then this, because we've divided by, or because we factored out that negative 1 divided by sigma squared, we're going to have to multiply each of these by negative sigma squared. So we'll have negative 4 sigma squared times x minus mu cubed. And then with this piece, we're going to have plus 12 sigma to the 4th times x minus mu. And all of that actually should be multiplied by that exponential. And we factored out the exponential, so it's gone. All right. Do we have any like terms? We've got, well, these are like terms. So I'm going to have negative 10 of those. And then these are like terms, so I'm gonna have 15 of those. Oh, tedious, isn't it? Okay though. I wonder if I feel like I've done this before as I was preparing the Desmos graphs. I don't remember it being that involved last time, or this involved last time. So I end up with x minus mu to the fifth. I've got -6 of those and -4 of those, so I'll have -10 of those. And then I've got 12 of these and 3 of those, so I'll have 15 of those. And say, okay, when is that equal to 0? That is equal to 0 at, or when this polynomial is 0, because this is non-zero and that's non-zero. So we want to factor that polynomial as much as possible if we can. Notice that we've got an x minus mu as a factor for everything, so we'll factor that out. And then we're left with x minus mu to the 4 minus 10 times sigma squared times x minus mu to the second plus 15. And that's quadratic in form. I just don't know. We have other two numbers that multiply to give us 15 that adds a 10. And actually, I think there's supposed to be a sigma to the 4th there. Because that was 3 sigma to the 4th times x minus mu and a 12 sigma to the 4th times x minus mu on the last page. I want a product of 15 sigma to the 4th and a sum of -10. I don't think we can get that. 1 and 15 won't work. 2 is not that function is not divisible by 2. Or that 15 is not divisible by 2. And then we have 3 and 5. 3 and 5 add to 8, not 2. So it doesn't look like that factors. Okay, well, if it doesn't factor, what could we do? We could complete the square. We'd say, well, what's half of 10? It's 5. And then if I squared that, what would that be? 25? So I'd need a 25 sigma to the 4th over here. So this could actually be x minus mu squared minus, what was it? 10 sigma squared times x minus mu squared plus 25 sigma to the 4th. And you would say, okay, well, isn't that a 15? Well, yeah. In order to make this equal to this expression up here, in order to make this a 25, or in order to make this last term or this last expression equal to this 15 sigma to the 4th, I just also need to subtract 10 sigma to the 4th. So I've got this is actually equal to this expression minus that 10 sigma to the 4th. We've got that, and then we've got those 2 extra factors out front. Sorry, this is so tedious. Okay, well, what is this expression? I've got a constant times an exponential, which is always positive, times x minus mu. And then this expression is something squared minus 10 sigma to the 4th. The last thing I'm squaring is a 5 sigma squared. So I'll have a 5 sigma squared here. Subtracting that because that's a negative sign. And then I'll have, this is an x minus mu to the 4th. So this is actually, excuse me, x minus mu squared. So I end up with x minus mu squared minus 5 sigma squared quantity squared. All of that minus this. Okay. And that is our factor that's multiplying that x minus mu. And that is times this equals that 5th derivative of f. And say, okay, well, when is that 0? Set this equal to 0 and solve for x. Well, this is never 0, this is never 0. This is 0 when x equals mu. or this expression is 0 when this perfect square equals that 10 sigma to the 4. Now, if I'm trying to get this x by itself, in order to get rid of that squaring function, I need to take the square root of both sides. Don't forget your plus or minus on the right. So we're going to end up with an x minus mu squared minus 5 sigma squared equals plus or minus the square root of 10 times sigma squared. And then we'll add this to both sides. So 5 sigma squared plus or minus square root of 10 times sigma squared, or if you prefer, 5 plus or minus square root of 10 times sigma squared. And we still have an x minus mu squared there. Trying to get x by itself, so we'll take the square root of both sides. Don't forget your plus or minus on the right. We end up with x minus mu equals plus or minus the square root of 5 plus or minus the square root of 10, and square root of sigma squared is just sigma. Since we have x equals the mean plus or minus this expression. All right. So I'd say, oh, how many x values is that? Well, that was a 5th degree polynomial, right? Because we've got a 4th degree polynomial here times this extra linear polynomial. So it's going to be a 5th degree polynomial. I'm expecting 5 roots. And these are the 5 roots. There's our first one. And then I'll call that x sub 1. X sub 2 comes from using a plus sign and a plus sign here. So we'll have the mean plus the square root of 5 plus the square root of 10 times sigma. Our next one, we'll use a plus on the first one and then a minus on the second one. That's our second and our third root. And then our fourth root comes from using the minus sign here. So have the mu minus in both cases. And then we'll have 5 plus the square root of 10 under that radical, and 5 minus the square root of 10 under that radical. And all of those are multiplied by sigma. So we've got those 5 roots. Ooh, Lord. Now we're interested in this interval from the mean minus 2 sigma, the mean plus 2 sigma. And so you say, okay, well, which ones of these are actually in our interval? Well, this is one of our x values that gives us that derivative of 0, or that 5th derivative of 0. Where the 5th derivative is 0, and that's a potential x coordinate of a relative extremum for the 4th derivative. So we'll evaluate the 4th derivative there and see what we get. Now, if I take 5 and then I add the square root of 10, and then I take the square root, I need to know, is that a number that is greater than or less than 2? Well, the square root of 5 is greater than 2. So anytime I've got the square root of 5 plus something, that's going to be outside of our range, outside of the interval of interest. So this 5 plus the square root of 10, and then we take the square root, that's going to be a number that's greater than 2. So that's beyond 2 standard deviations above the mean. So we don't want that. And we don't want this one either. I've got 5 plus the square root of 10. And then I'm taking the square root, so I'm subtracting something that's greater than 2 standard deviations from the mean. So that's going to be below that number. So that one's out as well. But square root of 10 is a little bit more than the square root of 9, which is 3, right? This is going to be like 3 point something. So if I take 5 and I subtract 3 point something, I'm going to get like 1 point something, and I take the square root. So this is actually in the range that we're interested in, and this is also in the range that we're interested in. So these x coordinates actually might correspond to relative maxes, or maximum, well, a relative extremum, excuse me, of that 4th derivative. So you say, okay, how do I know? Well, we plug those x values into the 4th derivative. We look at the y values, and we also look at the y values at the endpoints here and here. The largest y value on your list is the max. And of course, we're going to take the absolute value of all of those because we're asked for the absolute maximum of the absolute value of the 4th derivative, not just the 4th derivative. So you say, okay, well, what was the 4th derivative again? I know it's sort of tedious. Let's write that down. Now, if we evaluate this at the mean, this is e to the 0, which is 1. This is 0 to the 4th. This is 0 squared. And we just end up with 3 times that standard deviation to the 4th. So I end up with 1 times that 3 times the standard deviation to the 4th times this fraction. So we're going to end up with this. And 4 of those reduce. So you end up with 3 divided by that sigma to the 5th times the square root of 2 pi, excuse me. And say, okay, well, what about these two x values? Well, actually, let's do the endpoints next. Let's do the interior points. Sorry. We've got this coefficient. Then when I evaluate this exponential at this value, I'm taking the mean away from this. So I'm just going to end up with that number squared. So I end up with e raised to the square root of 5 minus the square root of 10 times sigma. All of that squared divided by 2 times sigma squared. And then when I subtract the mean again from the x's, all of that is times what I have down here. I end up with this square, or this to the 4th minus 6 sigma squared times that expression squared plus 3 times sigma to the 4th. And we just do a bunch of arithmetic, really. I guess it's algebra. Feels more like arithmetic, doesn't it? It's just computation. When I square this, I end up with a 5 minus the square root of 10 times sigma squared, all divided by 2 times sigma squared. The sigma squareds reduce, and you just end up with that square root of 10 minus 5 in the numerator. And then this, when I square that, I'm going to get that 5 minus square root of 10, but then I'm going to square it again, because I'm raising it to the 4th power. And then I have sigma to the 4th minus 6 sigma squared times, when I square that, I have 5 minus the square root of 10 times sigma squared plus 3 times sigma to the 4th. Now, if I square this, I'm going to have a 25 times sigma to the 4th minus 2 times 5 times the square root of 10. So it's going to be minus 10 root 10 times sigma to the 4th. And then the square root of 10 squared is going to give me a 10 sigma to the 4th. And then here, if we distribute that negative 6 sigma squared times sigma squared to that 5, we're going to end up with a negative 30 sigma to the 4th plus, actually minus, no wait, that's a minus and that's a minus. It's going to be a plus. Plus 6 square roots of 10 sigma to the 4th. And we're done with that term. And then we've got 3 sigma to the 4th. This is very tedious. Okay. So I've got 25 plus 10 is 35 sigma to the 4th. Minus 30 is going to be 5 sigma to the 4th. Plus 3 is going to be 8 sigma to the 4th. I did this before and I do not remember having to do all of this. I feel like I may have made a mistake. But then I've got negative 10 of those and 6 of those over there, so that's going to be negative 4 of those. And they both have a sigma to the 4th in common. We can factor out that sigma to the 4th. It will cancel with 4 of those in the denominator. So we'll have 1 divided by sigma to the 5th, which is square root of 2 pi times e to this power. And we'll have an 8 minus 4 square roots of 10 here. I guess you could put that in that numerator if you wanted to. All right. And then we do the same thing at the other one, which looks just like this, except instead of having minus that square root, we've got, or instead of adding that square root, we're subtracting it. So I'm looking through my calculations and I want to see how that changes things. If I have a minus here rather than a plus, I have a minus there. I'll have, when I substitute that mean minus this expression, it's gonna make that negative inside the parentheses, but then I end up squaring it. So that's going to stay exactly the same. And then here, when I do the x minus the mean again, that's gonna make that negative and that negative. Since I'm squaring that here and raising that to the fourth there and raising that to the second power there, I think everything should be exactly the same as before. Because when we square it, the negative times a negative makes a positive. And raising it to the fourth is going to make a negative times a negative times a negative times a negative makes a positive. So we're going to get the same value. So this is at both the mean plus and minus the square root of 5 minus the square root of 10 times sigma. Okay. And we're also interested in f at the endpoints, or the fourth derivative at the endpoints. So we need to evaluate at 2, or the mean plus or minus 2 times sigma. That's a little tedious. And there's my fourth derivative. If I subtract the mean from my x's, I'm gonna have plus or minus 2 sigma in the parentheses there. So we'll have e to the negative plus or minus 2 sigma squared divided by 2 squared sigma squared. And then this will be plus or minus 2 sigma to the fourth minus 6 sigma squared times plus or minus 2 sigma squared plus 3 sigma to the fourth. So you end up with e to the negative 4 sigma squared divided by 2 sigma squared. Those reduce, and we end up with e to the negative 2 there. And this will be 4 sigma to the 4th. And then we'll have 6 times 4 is going to be negative, or that negative 6 times 4 is going to be negative 24 sigma to the 4th. And then we've got 3 sigma to the 4th. That's negative 20 plus 3 is negative 17. End up with negative 17 sigma to the 4th divided by sigma to the 9th times the square root of 2 pi times e to the negative 2. And that will cancel with 4 of those, so we'll have 5 of those remaining in the denominator. All right. Now I'm looking at those values and I'm like, which one's the largest? I have no idea actually, because I don't really know how to approximate these things. I'd probably just use a calculator. Let's use the calculator to see which of these y values is the largest and the smallest on the interval from the mean minus 2 times the standard deviation to the mean plus 2 times the standard deviation. Since all of them have the same shape, I probably should have just used a mean of 0 and a standard deviation of 1. But I wanted to show you that even if the mean was non-zero and if the standard deviation was not equal to 1, that we get the same value anyway. That, well, the areas are the same. Now, what does that have to do with the second or the fourth derivative? Well, the fourth derivative ends up being written in terms of the parameters, but as far as the extrema are concerned, and the extreme values might also be in terms of the parameters, but the corresponding error is going to be the same. All right, I think it is. I think it's always going to be the same. All right, so let's look at those values. So these are our three values. One thing I want you to notice about all of them is they all have that sigma to the fifth and that square root of 2 pi in common. So when I'm comparing them, I'm really just comparing the extra factor. This is 1 over that sigma to the fifth times the square root of 2 pi times 3. And this one is that sigma to the fifth times the square root of 2 pi times a negative 17 divided by e squared. And then this one is the sigma to the fifth times the square root of 2 pi in the denominator times this 8 minus 4 times the square root of 10 times e to this power. And so really you're just comparing those three numbers, the 3, that, and that. The largest one is going to be the maximum, or is going to, well, be the maximum value of the fourth derivative on the interval of interest. So when I compare that 3 to the negative 17 over e squared and the 8 minus 4 times the square root of 10 times e to the square root of 10 minus 5 all divided by 2. When I compare those values, I have a 3, a negative 2.3, and a 1.85. When I take the absolute values of all of those, the largest one occurs at 3. So that's telling me that, and that 3 corresponded to the mean, so that the fourth derivative of the original function at the mean was 3 divided by the sigma, or the standard deviation, to the fifth times the square root of 2 pi. So the maximum is going to occur at the mean. Now we can see that if we just graph these functions. So here's our second derivative. And there's our third. It's kind of cool. We say, okay, well, where is then we look at the fourth derivative. And if we look at that, I only want to, let's look at this for a smaller range of x values. Let's go from negative 3.5 to 3.5. We see we have a maximum at the mean. And in this case, the mean is 0. But if we look at the absolute value of that function, it looks like that. And now we can see that on the interval, we actually had a maximum here, a relative max here, a relative max here, or the original function had, whoops, a relative min there, a relative min there, and a relative max there. But then we had to take the absolute value. And so I got that this was the a max, and that was a max. And then we had these values at the endpoints. And then we had that value in the middle. So those are actually the 4 values we checked. I know that it didn't look like that on paper, but we looked at the fourth derivative at the mean, which is in the middle. And then we looked at the fourth derivative at the endpoints. And then we looked at the fourth derivative at this x value and this x value. At these 2 values, we got that 8 minus 4 times the square root of 10 times e to the square root of 10 minus 5 all divided by 2. That times that 1 over sigma to the fifth times the square root of 2 pi. Anyway, it's just a number, right? We can just look at the graph and we see that the maximum occurs at the mean. So that's what we get. That's our maximum value for a standard deviation of 1. And we say, okay, let's look at that error formula now. So our error formula said the upper bound, or n upper bound for the error, is b minus a to the fifth. And b minus a in our case is the mean plus 2 standard deviations minus the mean minus 2 standard deviations. So it's actually going to be 4 standard deviations to the fifth divided by 180 times n to the fourth, where n is the number of subintervals that we need, times this maximum. We found the maximum in terms of the standard deviation, and we can simplify this expression as well. So that upper bound for the error, I'm doing this on paper, . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . is the mean plus 2 standard deviations minus the mean minus 2 standard deviations, all to the fifth, divided by 180 times n to the fourth, times the maximum value of the fourth derivative, or the absolute value of the fourth derivative. That's going to be a sigma to the fifth, or 3 times the sigma to the fifth divided by 2 pi. And if we do those calculations, we end up with that 4 sigma to the fifth here. 4 to the fifth is this 1024, I believe. That's our 1024. That 3 goes into 180 60 times. The sigma to the fifth from this numerator and the sigma to the fifth from the denominator, they cancel. And then you just end up with that square root of 2 pi. So after simplification, what we get is 256 divided by 15 n to the fourth times the square root of 2 pi. And we want that to be less than 0.0001 in order to guarantee that our error is less, or our error in the approximation using the Simpson's rule is less than that desired error. And I'll do that pencil and paper calculation now. So we're going to multiply both sides by this. Divide both sides by 15 times the square root of 2 pi. And I want to take the fourth root of both sides, or raise both sides to the 1/4 power, same thing, right? And this is going to tell us n has to be greater than some number. I'll use the calculator to find out what that number is. And then we'll know that if we take that many subintervals, or a larger number of subintervals than that, we can get the error within the desired, or we can get the approximation to be within 0.0001 of the actual value. So if we do that calculation, we see that our n value has to be greater than approximately 16.15. So, and our n value needs to be even. So the largest or the smallest n value that's greater than 16.15 that's even is 18. So if we use n equals 18 subintervals, then we'll have an error less than 0.01. So we've got that interval from m minus 2 times, or the mean minus 2 times the standard deviation to the mean plus 2 times the standard deviation. So basically the length of the interval is 4 times the standard deviation, and we want to divide that by 18. 4 times the standard deviation divided by 18 is going to give us 2/9 of the standard deviation. So when we come up with our 18 values, we're going to start at the mean minus 2 times the standard deviation, and every time we go from piece to piece, we're going to add 2/9 of the standard deviation. So we've got the mean minus 16 over 9, minus 14 over 9, minus 12 over 9, minus 10 over 9, and so on, minus 8 over 9, and 6 over 9, and you just keep adding 2/9 of the standard deviation to get all of those function values. There are 18 of them. And then as far as the coefficients are concerned, remember with Simpson's rule, we had that equation that told us that the area under the curve for a polynomial, where that we're talking about a second degree polynomial from x equals a to x equals b, was like some number times the value of the polynomial at the left endpoint plus the value of the polynomial at the right endpoint plus 4 times the value of the polynomial at a minus or a plus b divided by 2. So the average x value on that interval. Using that on every 2 subintervals, so we're using 3 points, means that we end up with these coefficients of 1, 4, 1 on every set of 3 points. On the interior points, that the ones that are counted once on the very end are counted as an endpoint for that first double subinterval, and then as the beginning point for the next double subinterval. So we end up doubling those. The only function values that we only count once are the ones at the very end and the very beginning and the very end. So the coefficients are always 4, 2, 4, 2, 4, 2, 4, 2, and then the last one is a 4. And then the first coefficient is 1 and the last coefficient is 1 for the function value at the very beginning and the function value at the very end. And then Simpson's rule says what you want to do is you want to take 2 times delta x, which is, in our case, this m minus 2s minus m plus 2s, that's our b, minus our a, divided by, what was that, 18? That's the length of our subinterval, and then we end up taking 1/3 of that for the coefficient out there. And with 18 subintervals, this is what we get. Now, if I wanted to graph that and show you what that looked like, I would actually have to divide this interval from the mean minus 2 standard deviations to the mean plus 2 standard deviations, or just alternatively, we could just look at x between -2 and 2, right? And then divide that by 18. And then at each of those values, we'd find the corresponding y values. And then, of course, the area under the curve is going to be equivalent if we change the mean or we change the standard deviation, because all of these normal distributions have basically the same shape, but we change the parameters, which are the mean, that measure of center, and then the standard deviations, which just spreads things out or makes them very skinny if the standard deviation is less than 1, and it makes them very broad if the standard deviation is greater than 1. But with 18 subintervals, we'd have to find 9 polynomials. It's not that difficult to do, but it's kind of a pain, so we won't actually do that. But if we want to have an error that's less than 0.0001 of the exact value of that area under the curve, we could use Simpson's rule with n equals 18, according to our upper bound, that formula that we have for the upper bound for the error. Now, the actual error when n equals 4, so we only had 2 polynomials, or was it 2 polynomials? Was 0.007. We might be interested in what we get when n equals 8 rather than 4. So I'm going to do that in the next one. And we're not going to go through as many details. I just want to graph it for you. Same concept, we're just going to use n equals 8 rather than n equals 4. Then we'll have 4 polynomials. So instead of taking the 3 points at -2, -1, and 0, now we're going to take 3 points at -2, -1.5, and -1, and then -1, -0.5, and then 0, and then 0 and 0.5 and 1, and then 1 and 1.5 and 2. But we're writing those in terms of that mean minus a certain plus or minus a certain number of standard deviations. So that's what we see in our table of values each time. So we do the same thing that we did before. Want to plot those points. And so we've got those 3 values there. And that's our polynomial approximating the function there with those 3 points. And you can see that green function is almost identical to the original curve. Then we find the exact area under that polynomial, and we say that that's approximately equal to the area under the original function. Then we do the same thing on the next subinterval. So now we're using these 3 points. So then we have this polynomial approximating our function. It's not as good of a fit, but it still fits those 3 points. And then we find the area under the curve. And then you do it again. Next 3 points. And actually, we're solving a system of 3 equations and 3 unknowns, so we could do some pre-calc if we wanted and find those A, B's, and C's ourselves. Since we know how to do it, we'll let the calculator do it for us. My thought with the students is, if you know how to do it by hand, you can use technology to do it. But if you don't actually know what the technology is doing, if the technology is a black box that does all the work for you, then we want to make sure we understand that. So That's when I do the pencil and paper calculations to make sure we understand what we're getting. Then once we know how to do that, then we can let the technology sort of do the sort of tedious part, and we'll just do the thinking part. So this is the area under the curve with 8 subintervals rather than 4. So I used 3 points here, 3 points here, 3 points here, and 3 points here. And so the x value at -1, or the function value at -1, 0, and 1 was counted twice. So then when we use Simpson's rule, those are the ones that are doubled. And if you look at the code for Simpson's rule with 4 versus the code for Simpson's rule with 8, it's pretty much the same. Here n equals 4 and here n equals 8. I just have 9 terms on my list rather than 8, or rather than 5 terms on my list. I always have n plus 1 terms. Because you got that first one, which we call that first x value, which we call x of 0, and the last one is x of n. And we see with 4 subdivisions, we have 0.94 as the area approximately. And with 8, we've got 0.9544. Now, Desmos already knows how to calculate that. And I believe all of these digits are correct all the way out to here. So Desmos, I don't know how Desmos is calculating that. I'm actually very curious. But it's giving us an exact answer out to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal place. So if we look at the difference between that and our approximation using 8 subintervals, we see our error is less than 0.00009. So it's even less than that error that we wanted. We didn't need to use 18 subintervals to find an excellent approximation to the value of that integral. We could have just used 8, and that would have been sufficient on the last one. But we didn't know what would be sufficient in advance, or we wouldn't necessarily know what would be sufficient in advance if we didn't already know what the value of that integral was. Since we have a calculator that can compute the value of that integral out to the 12th decimal place for us, we could have just computed our approximation using Simpson's rule and then took the difference between the actual value and our Simpson's rule approximation to find the error. But usually when we're using a numerical method, it's because the computer doesn't know how to solve it numerically. I don't even know if that's a good thing. Like, why would we use that if the computer knows how to do it? I guess somebody has to know how to program these computers, right? So it's important that we have some sense of where these numerical methods come from. I'm just curious about how the computer is doing that. Okay, so we do all of that we did before. We talked about it already. And then the error with 18 subintervals is less than 0.000003. So it's even better than when we had 8. But again, we did not graph those 9 polynomials. We could have, but we just didn't. All right, so that's that. We've talked a little bit about this. Now, if you're curious about this probability distribution, I highly recommend that you take a statistics class. You can learn how the area under this curve is related to probability that a particular normally distributed random variable lies in some interval of values. I'm going to go from, let's see, 0.2 to 0.5. There we go. So that's pretty. But you can do that in elementary stat. Since we're in calculus, we wanted to do a couple of things. We wanted to graph the function, and we did. And we wanted to estimate that area under the curve. And since we didn't have a rule, we don't have a rule for taking the antiderivative of e to the negative x squared. This is what we have to do at this point, given the tools that we have in order to approximate that area under the curve. So I hope you enjoyed that. Let me know if you have any questions about either that those 2 numerical integration techniques, or curve sketching, finding points of inflection, relative extrema, and intervals where the graph is increasing or decreasing, or the function is increasing or decreasing, or the graph is concave upward or concave downward.